Hey guys, this is Professor Janacek, and I want to continue our conversation about integration by substitution. This time I want to look at definite integrals. The main thing to remember about a definite integral is that when we rewrite it in terms of our variable u, we also have to update our limits of integration and figure out what the new values will be, the u values, if you will. So let's dive in and take a look at some examples so you can see how this is done. So example 5 here, we're going to integrate from 0 to 2 of dx over x plus 3 cubed. I think to begin with, it'll be nice to go ahead and rewrite this in the form of x plus 3 to the negative 3 power, and then push that dx off to the side. This will allow us to kind of think of it in terms of the power rule. All right. Remember, with u-substitution, we look at our integrand as a composition of functions, and in this case, I think we'll want to let u be that inside function x plus 3, then du is simply, let's see, the derivative of x is 1, the derivative of 3 is 0, but we still have that dx in there. Again, we're finding du, not just du dx. Okay, so I think this will allow us to make our substitution. We're going to integrate u to the negative 3rd power, and then in the back dx, that's just du. Now, the one thing that we really have to concern ourselves with is that we do need to change those limits of integration. We cannot leave them from 0 to 2 because those are x values. We are looking at u values. So, for x equal to 0, u is equal to 0 plus 3, or 3. And for x equal to 2, u, again, 2 plus 3 actually gives us 5. So now we are integrating, instead of from 0 to 2, we're going to integrate from 3 to 5. Now, it is possible to leave x values, and then when you get to the end and rewrite your the expression in terms of x, to evaluate it with your x values. However, it is never good notation to leave 0 and 2 there. If you want to do that, you could have instead written this as, say, u of 0 and u of 2, u to the negative 3 du. So you are welcome to use that notation. However, you cannot just leave 0 and 2. There are other notations that are not very appropriate. Remember, this is all in terms of u, so I really can't reference the x's. I can't say put x values here. I have to have u values. All right, but I'm not going to use this version. I'm going to just stick with this version here. So now if I integrate u to the negative 3 du, we end up with, let's see, that'll give us, what, negative 1/2 u to the negative 2. And this gets evaluated from 3 to 5. So that is negative 1/2. Actually, let me write this as negative 1 over 2u squared evaluated from 3 to 5. I think that's going to make it a little bit easier. So that is negative 1 over 2 times 5 squared minus, remember, fundamental theorem of calculus says it's going to be minus, and then a negative 1 over 2 times 3 squared. It's negative 1 over 50 plus 1 over 18. 18. So what does that give us? Oh, in the numerator, it's going to be 18, negative 18 plus 50. Oh. The common denominator, of course, is 18 times 50. So what does that give us? 32 over, oh, we'll be able to reduce that. 18 times 50, I'm just going to reduce. Oh gosh, if I reduce by 4, that means I probably reduce by more than that. Maybe not. If I reduce by 4, that gives me an 8 in the numerator. I'll reduce the 18 by 2 is 9. 50 by 2 is 25. And you could do this, however, there are all kinds of ways of going about this computation. So we end up with 8 over 225. All right, I think that looks pretty good. Okay, now on to example 6. Let us integrate from 0 to 4 of x over x squared plus 1 dx. I'm going to again start by rewriting this as x squared plus 1 to the negative 1 power times x dx. If we let u be that inside function x squared plus 1, then du is 2x dx, which works out fairly well. I will need a 2 back there. So we have x squared plus 1 to the negative 1. We need a 2x dx. So I'll have to balance this by putting a 1/2 there in the front. But now I think we're ready to rewrite this in terms of u's. Remember, for x equal to 0, u is going to be 1. And for x equal to 4, u is going to be 17. So now we've got the 1/2 in front still. Instead of going from 0 to 4, we're going from 1 to 17 of u to the negative 1 du, which u to the negative 1 is 1 over u. You might recognize it in this format. If you integrate 1 over u du, we end up with the natural log of the absolute value of u, although I notice that my u values are both positive, so I'm not going to worry about that absolute value. And then we'll evaluate that from 1 to 17. So that is 1/2 times the natural log of 17 minus 1/2 times the natural log of, actually, you know what, I'm going to do it this way. Well, no, this works. 1/2 natural log of 1. Okay, I can work with that one. Natural log of 1 is 0. So that just gives us 1/2 times the natural log of 17. Ah, that wasn't so bad. All right, let's take a look now at example number 7. Hopefully my battery will hold out. Let's integrate from 0 to pi over 2 of sine to the 4th x cosine x dx. So I think the first thing I'll do is again just rewrite this so there's no confusion. This is sine of x to the 4th power cosine x dx. We will let u be that inside function, sine of x. Then du, the derivative of that is cosine x dx. This works out wonderfully. We are integrating u to the 4th du. Now we will have to change those limits of integration. For x equal to 0, u is the sine of 0, which is 0. And for x equal to pi over 2, that upper limit of integration, u is the sine of pi over 2. Sine of pi over 2 is 1. So we're now integrating from 0 to 1 of u to the 4th du. Oh, well, that's a simple one. U to the 4th du, when we integrate that, we get u to the 5th over 5. We're going to evaluate this from 0 to 1. So that gives us 1 to the 5th over 5 minus 0 to the 5th over 5, which looks like it simplifies to just 1/5. Well, there we go. Enjoy.